Hi everyone. Today I'm going to demonstrate how to provide OSHI functionality through a bare metal switch. For this experiment, we choose to use a Pica8 P3922 switch using the Pica8 operating system. Pica8 is able to talk to the hardware platform and switch the packets in hardware using OpenVSwitch, which is one of the basic components used by the OSHI nodes. As you can see, when I open the CLI of the switch and I type OVS vsctl show, the CLI shows us the default bridge already created on the switch. In the interest of time, I added already two physical ports to this bridge, TE111 and TE112. I also added two more internal interfaces called Quagga01 and Quagga02. We need now to install the second component, Quagga. To do that, it's very easy. You just need to go in the CLI and type sudo apt-get install Quagga. In the interest of time, I've already done this, and Quagga is now installed and ready to go on the machine. The next step would be to configure the configuration files of Quagga in order to let it connect properly to OpenVSwitch. The configuration files of Quagga can be found in etc Quagga. As you can see, I already placed all the configuration files needed in this folder. Let's have a look specifically to a couple of these files, starting with zebra.conf. Inside zebra.conf, which include the main configuration of Quagga, I inserted the two virtual interfaces I created before in the OpenVSwitch bridge, and I gave to each of them a specific IP address in a different subnet. Specifically, Quagga1 has the IP address 192.168.0.1/24 and Quagga2 has the IP address 192.168.1.1. Let's take now a look to ospfd.conf. Since we want to simulate the behavior of a router, the intention here was to enable OSPF on all the interfaces. What we do basically is to say that we want to include these two interfaces in the OSPF configuration and we want to advertise hello packet through those interfaces. And then we also say that we enable OSPF on these interfaces and we want to announce these two networks through them. At this point, we just need to start the Quagga service, typing sudo service quagga start. In our case, the service is already running. I can show it through psiux grep quagga. As you can see, there are two main daemons running that we configured before, which are Zebra and OSPFD. From a switch perspective, the last thing we've got to do is to create the proper flows in order to discriminate between the OpenFlow traffic and the traffic that instead needs to be routed in a legacy fashion. In this experiment, we'll do this thing through the usage of VLAN tags. The flows can either be installed by an external controller or, as in this case, manually directly on the switch. Typing the command ovs ofctl dump -flows and then the name of the bridge, which in our case is BR0, we can see all the flows that have been already installed on the system. Specifically, as you can notice, the first two flows in our case match on the destination VLAN 100. These flows will be used to connect the two physical ports of the switch. So basically, all the traffic that will come inside the switch matching on VLAN, destination VLAN 100, will be just treated as OpenFlow traffic and will be managed just by OpenVSwitch. Instead, the last four flows are used to link together the physical ports with the virtual ports in both directions. So all the traffic that won't be tagged with VLAN ID 100 will just go to the router and will be treated as a legacy traffic. Let's move now to the clients directly connected to the switch. Moving to client 1, typing ifconfig, you can see that I have an interface ETH1 that has an IP address able to talk to the address that we configure on one of the two interfaces of the router. Please notice that this interface is completely untagged. On top of the same interface, we create also a tag interface eth1.100. We gave to this interface another IP address in a completely different subnet from the previous one. In exactly the same way, we did the same thing with client 02. Of course, in this case, we give to eth1 an address able to talk to the second interface created in Quagga. In the same way, we gave to the interface eth1.100 a second address able to talk to the first address configured on the tag interface on client 1. At this point, the very first thing we can show is that both of the clients are receiving the OSPF hello packets from the Quagga router. So to do that, we can TCP dump on eth1, which is directly connected to open the switch, with that then is connected to the router. Okay, so we receive OSPF hello packets on client 1. We can show the same on client 2. Here we go. This means that potentially we can directly attach to our bare metal switch directly another router that talks OSPF and exchange route advertisement with our Quagga instance. Let's try now to ping between the two clients. So first of all, I want to ping between the two untag interfaces, sending my traffic through Quagga that will route the traffic between the two hosts. As you can see, the host 1 is able to talk to client 2 through the untag interface, which is connected to OVS and Quagga. Exactly the same way, I want to demonstrate that client 1 is able to talk to client 2 through the tag interface, which uses just OVS and OpenFlow rules. As you can see, also in this case, the two hosts are able to talk together. In this video, we demonstrated how to enable the OSHI functionalities on a Pica8 bare metal switch, thus being able to switch the OpenFlow packets in hardware and at the same time provide legacy routing functionalities in software. We hope it's been useful as an example for all of you. Thank you, and see you next time. Ciao!